hybridization. Now, what is hybridization? Hybridization, simply put, it's the blending of orbitals on the covalent bonds. It's important to note that bonding occurs when half-filled orbitals overlap. Now let's look at this overlapping. If we have a hydrogen over here and we have a chlorine on the other side, we know that hydrogen has a 1s orbital with that lone electron, positive spin upwards, and then chlorine ends with a 3p. 1, 2, 3, 4, 5. So this one, almost stable, just needs to share an electron for this half-filled orbital, right? So right now this is half-filled. It wants to overlap, let's say with this one over here, so it wants to overlap as such so that both can be stable, so that this one can be happy, and same thing for this one. Again, we're dealing with covalent bonds, right? We're only sharing electrons. And if we have our hydrogen here, let's say, and our chlorine, let's say over here, okay? The overlapping, again, chlorine's like this because of the 3 different positions that it can be in. So let's say they overlap right over here. And if they overlap over there, this, based on what you can see here, is known as the valence bond theory. And it's a simple illustration. It's kind of like a Venn diagram. There is an area between here that they have some similarity. And then this is where they are sharing that lone electron. So this one is going to be shared with that one so that this whole thing can become happy and stable. Again, it's happening right over there. Now, if we look at, let's say, another example of, let's say, CH4. The problem with the valence bond theory is an example like methane doesn't really work out very well. So if we look at our carbons here, and we have our hydrogens. Again, this is the tetrahedral shape. This carbon, again, has these electrons. And of course, so do the hydrogens as well. Okay, let's deal with the central atom though first for the carbon. It's 1s, it's 2s, 2p. Let's count 1, 2, 3, 4, 5, 6. So carbon here on its valence, right, has 2. So carbon only wants to share 2 electrons, but experiments show that it makes 4. Again, I know this whole thing here is the valence electron, but these are the only ones that are unfilled. Okay, bonding occurs when half-filled orbitals overlap. So this needs to overlap with someone, and this needs to overlap with someone. Then it can become happy. But again, like I said, the experiments show that it makes 4, not 2. Again, we should be seeing 2 of these, but we don't. We be seeing 4. Why is that the case? This is because of hybridization, and that there are hybrid orbitals that blends the orbitals on these covalent bonds. So rather than just having these, all 4 actually end up becoming the bonds. And we have to always look at the central atom that does this. So because carbon is that central atom in our example here of methane, it has hydrogens too. 1, 2, 3, 4 hydrogens. So we got to draw 4 hydrogens. All right, so we have a hydrogen here. Okay, we have another hydrogen here. We have another hydrogen here, and another hydrogen here. All 4 of these need to be bonded with those 4. But we can't illustrated this way because these are already paired up together. If these are paired up together, then how would all 4 of these be bonded? Because obviously every single one of these hydrogens want to become stable too. So we need to change our illustration here. So what we need to do is, for this methane, change our shape so that all 4 of these have a good equal opportunity to bond. Now it's going to be important for us to remember this. Linear shapes have a 2sp. It's very, very important that you all memorize this. So linear has a 2sp, trigonal planar, ends up having a 3sp2. Then we have a tetrahedral. Tetrahedral is 4sp3. And then we have our trigonal bipyramidal. And that is 5sp3d. And then lastly we have octahedral. And that's 6sp3d2. And we need to figure out what we are dealing with. Remember, we drew the carbon and the hydrogens in such fashion because we know that it's a nonpolar molecule and it has symmetry. You can look at the previous video regarding this for the polar versus nonpolars if you're still confused why this is nonpolar. Our carbon in the middle needs to change its orientation. Before we do that, we have to look at what type of shape it is. It is going to be a tetrahedral because there are 4 different bond segments. If there was, let's say, BH3, this is 1, 2, 3, this would be a trigonal planar, right? But because we're dealing with 4, 1, 2, 3, 4, we're going to be dealing with tetrahedral. If you see 5 bond segments, then it'll be 5, then it'll be trigonal bipyramidal, and if you see 6, then it'll be octahedral. Now with our methane, let's get our carbon ready. Our carbon is going to be looking like a 4sp3, meaning that there are going to be 4 of these orbitals, and each of them is going to be labeled as an sp3. sp3, 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 and sp3. The carbon, this whole thing, like I said, are the valence electrons. And we're going to ignore that only 2 wants to be bonded. We're not going to look at that. We're looking at a new concept. So we're looking at all the electrons of the valence. So again, we have 4. How are we going to spread them out? Well, all 4 spreads out very evenly. So it's a perfect example. And all 4 of these electrons want to bond with these hydrogens. Bonded, 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 bonded. That's pretty much it. And what we need to not forget is what types of bonds are present. Well, we have all of them becoming sigma bonded because anytime we have only a single bond, it's going to be sigma. If we have a double bond, for example, one of them is going to be sigma. That's by default. And then the one after, it's going to be a pi bond. If we have a triple bond, for example, then one of them is going to be sigma, other one's going to be pi, and the other one is also going to be pi. Okay, but one of them has to be sigma first. Sigma bonds are direct crossovers. This is why they're going to be strong. And then this pi bond here is a sideways crossover, so it doesn't cross over or overlap as much. Doesn't overlap between the orbitals as much, so it's not as strong. So I guess for layman's terms, we can just put weak, okay, for that pi bond. All right, so strong versus weak. CH2O. How are we going to start this off? Well, we know what type of shape this is, quite obviously. We have 1, 2, 3. And remember, a double bond still counts as just one segment. So 1, 2, 3, so there is 3. So obviously that's going to be our trigonal planar. It's going to be a 3sp2. So our central is going to be a 3sp2 orientation. So let's draw this out. We know that a carbon is a 1s, 2s, 2p. And the hydrogens are the 1s's. And then we have an oxygen. We can actually draw out the whole thing if you would like. So this is our oxygen. And when we bond these together, we have to think about how they are going to orient themselves in order to do this bond. So before we do any sort of illustration, we need to first write out our 3sp2, because that's how it's going to be orientated for the central atom. So the carbon is going to be in a 3sp2, so there's going to be 3 sp2 orbitals. So let's just draw 3 of them. 1, 2, 3. And each one is going to be labeled as sp2. And carbon over here, interestingly enough, there are 4 electrons. The issue, though, is that there are only 3. This means that one of the orbitals is not going to be an sp2. So these 4 electrons need to orient themselves this way. 1, 2, 3. Again, 3 of them are going to be sp2s. One of them is not. Now let's draw out our hydrogens and our oxygens. And I'm just going to bring our hydrogens a little bit closer. All right, again, these are our hydrogens. All right, and this here is our carbon. And of course, here is our oxygen. And when we put these together, let's put our single bonds first. And if there's only single bonds, it's always going to be a sigma bond. It's going to be very powerful. It's going to be very strong, strongly held. So this over here, let's say, goes with this hydrogen. It's going to be automatically a sigma bond. Let's do the same thing for this one. Automatically a single sigma bond. Now we have to look at the last leftover, our double bond. Remember, the first one of that double bond must be a sigma bond. After that, you can have pi bonds. So this one over here is going to be our first bond within that double bond. Of course, it's going to be sigma. That means this one over here is going to be our pi bond. And technically the pi bond doesn't really look like this. The pi bond is kind of on 2 sides, but we'll talk more about this when we get to the Vesper shapes. For simplicity's sake, let's just label it this way. So we have 3 sigma bonds and 1 pi bond. This is how it looks like. So there's a trigonal planar shape. And then there are 3 sigma bonds. And then there's 1 pi. Now let's look at C2H2. We have a triple bond, which means one of them is going to be sigma, the other 2 are going to be pi. Our carbon, like always, it's going to be a 1s, 2s, 2p. We got two of them. And we have two hydrogens. Let's figure out what's going to happen next. This is a linear shape because all of this is just one segment. All of this is one segment. So this would be a linear shape. So we're looking at a 2sp. So one of this is going to be an sp. The other one is also going to be an sp. We have to look at our other carbon because there are two carbons in question. So we'll put them in opposite directions this way. I like to outline it this way. You don't have to if you don't want to. So we have a carbon, two of them wanting to bond. This one as well, two of them wanting to bond. However, what about the other bonds? For this one and this one, they need to be present as well. So if there are two more electrons here, they need to be represented as well. And if there are two more electrons here, they need to be represented as well. Now let's put them together. Our hydrogens are still over here. We can't forget about those. So again, these are our carbons. These are our hydrogens. And we need to start putting them together. Our first bond over here must be sigma. So let's have this one bonded here as a sigma bond. What's going to happen next? Well, our double bond here is going to be a pi bond. So that pi bond is going to be bonded where? That pi bond, oh sorry, I forgot to add these two electrons. These two electrons need to be here. Okay, these two electrons are here, and these two electrons are here. All right, so they need to be bonded as a pi bond. So we're going to put this one with that one. That's going to be pi bonded. And we can do the same thing for this one as well. This one here is also going to be pi bonded. So we have a sigma and a pi and another pi. The only thing we have to deal with now is a strong sigma bond here and a strong sigma bond here. It does work out pretty well because this one can become sigma bonded, and this one can also become sigma bonded. So this is how it looks like. This linear shape has 1, 2, 3 sigma bonds, and then there's also 2 pi bonds and 2 pi bonds. So please try these review questions, our green questions of the day. Try the hybridization for these compounds in question: phosphorus pentachloride, xenon tetrafluoride, and hydrogen cyanide. And for each one, state the shape of the molecule and indicate the sigma and pi bonds that are present. Please pause the video, give it a try. I will show you the answer shortly. These are the answers.